Hello everybody, welcome back to the Gregorius Maths video. Today we're going to be looking at quotient spaces. Last time we looked at product spaces, now we're going to be looking at quotient spaces. So to get the hang of the idea of a quotient space, we'll begin with an in-depth example. Okay? So consider the 2-disk, which is equal to the set of all x, y in R2 such that the square root of x squared plus y squared is less than or equal to 1. Okay, so the boundary of the 2-disk, literally written like a partial derivative. It's got nothing to do with partial derivatives, it's just the way you denote the boundary. The boundary of the 2-disk is precisely equal to the 1 sphere. Okay? So the boundary is just the circle, the unit circle. Okay? So yeah, boundary is just the circle, the 1 sphere. Okay? So the quotient space, the 2-disk mod the boundary of the 2-disk, the quotient space is what occurs when we treat all of the points in the boundary as equal. So we have all the points in the boundary and we draw and we pull a draw chord, I think that's what it's called, up. So if you can imagine there being a point up here on the top of the sphere, and you kind of pull it up so it becomes a sphere, and all the points on the boundary get mapped onto this point, call it star. Okay? That's what's happening. You pull it up, basically. And all the points on the boundary are equal because they get mapped onto the same point. Okay? So what are we actually looking at concretely, now that we kind of know what we're talking about? Intuitively, a couple of things, well, a certain thing should be true. The 2-disk mod the boundary should be homeomorphic to the 2 sphere. That's what I was trying to say. It gets pulled, kind of, into the 2 sphere. So we have these, you just draw it tight. So if you can imagine this becoming a sphere, basically, and all the points on the boundary get put onto to a certain point. Okay? So, for example, if we have a function pi which takes us from the 2-disk to the 2-disk mods the boundary. Okay? The 2-disk mod the boundary is literally a set of all points. Well, not the set of all points. It's the 2-disk minus the boundary. And then you take what's called the disjoint union with this other point, star. Okay? That's what this is. Okay? So if you have a function which takes from the 2-disk to the 2-disk mod the boundary, okay? Is defined as follows: pi of x equals x, okay, if x is in the complement of the boundary. So it's in the 2-disk, but it's not on the boundary. So it gets mapped onto itself if it's not on the boundary, okay? And pi of x equals star if x is in the boundary. Okay? This is all good, but how do we actually make this topological space? Right now there's just some cool stuff we're messing around with, basically. But we want to formalize this to make it a topological space. We want to generalize this. Well, in this example, U, a subset of the boundary, of the two-disk mod the boundary, U, a subset of that, is open if the preimage of U under pi, okay, preimage of U under pi is open in the two-disk, okay? So, now that we've got that example in depth, hopefully you can basically see that it makes sense. Hopefully the generalized version will make complete sense to you. Okay? So if we have X mod A, now, again, this is equal to X minus A, and then you take the disjoint union with some point, let's call it star. Okay, so it's X minus A, disjoint union star. Okay, and now we define a function pi, which takes you from X and maps onto X minus A, disjoint union, the star. Okay, we have a function which takes you from there to there, defined as pi of X equals X if X is in X minus A, okay, and pi of X equals star if X is in A, okay? So if we relate this back to our original example of the boundary of the two-disk, okay? Well, if we had pi of X equal to X if X was in the two-disk but not on the boundary, and we had pi of X equal to the star if X was in the boundary, okay? And considering the open sets, okay, we have U, a subset of X mod A, open if, again, the preimage of U under pi is open in X. Okay? So now let's look at an example. An example. So an example of one of these quotient spaces, X mod A, is if we take a look at X equal to the closed interval between 0 and 1 squared, and by squared I mean the Cartesian product, so really I mean 0, 1 cross 0, 1, okay? But it's easier to write it like that, okay? Now, this means that A equal to the boundary of X is equal to the set of all X, Y, set of all X, Y in R2, okay? Set of all X, Y in R2 is such that X times 1 minus X times Y times 1 minus Y is equal to 0. Okay, and now we want to prove that X mod A is homeomorphic to the two-sphere. Okay? All we have to do is actually show that X mod A is homeomorphic to the the two-disk mods the boundary of the two-disk. Okay? So we'll have a little proof of this last statement here, okay, if we define f, which takes you from x to the 2 disk, as f of xy, f of xy equals the square root x squared plus y squared over the maximum of the absolute value of x or the absolute value of y, of xy. Okay? And the great thing about this is that the boundary of x maps onto the boundary of D. And so this is amazing. So we've already found our homeomorphism f. Okay? I'll leave it to you. Okay, and if we have the inverse, all we have to verify is the f inverse, which takes you from the 2 disk to x, defined as f of, the inverse of f of xy is equal to the maximum of the absolute value of x or the absolute value of y divided by the square root of x squared plus y squared of xy. Okay, so it's continuous, thus x over a is homeomorphic to the 2 disk mod the boundary of the 2 disk, which is homeomorphic to the 2 sphere, and therefore x mod a is homeomorphic to the 2 sphere. Okay? So, now that we've shown that, that's a quick example. Now, let's look at something slightly more general than the quotient spaces we've defined so far. Because so far, we've defined quotient spaces to map onto itself or map onto a specific point, star, let's call it, okay? But what if we want to make the the square, we want to glue it together to make a cylinder? Well, then we don't want to map the points on the square onto a specific point on the cylinder. We want to map each point on the edges of the square onto the edges of the cylinder. Okay? And for this we have to define an equivalence relation. Okay? So if we take a quick look at an example, the precise example that I've just been saying. Okay? So, if we have x equal to the closed interval between 0 and 1 squared, and tilde, the equivalence relation is defined as follows. Okay, the equivalence relation is defined as follows. xy is tilde, I'll just say tilde, x prime, y prime, okay, is equivalent to saying that either x equals x prime and y minus y prime is in the integers. Yeah, that's what it's saying. Okay, so it maps every point x of x onto itself, but it maps every point y onto either 0 or 1. Okay? So the following result, x mod tilde, should be homeomorphic to the cylinder, which I'll just call C. Okay, so with this new, more general construction, it turns out that this gives rise to a lot of quite cool spaces in topology, I'd say. Pretty, yeah, just cool and kind of important. I don't know. For example, the Mobius strip is defined via the quotient spaces. So yeah, we have the Mobius band, which you should probably be familiar with. It's quite a famous thing in, well, just maths. Okay, is defined with the same, we have the same x, the closed interval between 0 and 1 squared. If we have x, y, tilde, x prime, y prime, okay, equivalent to saying either that x, y is equal to x prime, y prime, or x equals 1 minus x prime, or y minus y prime equals plus minus 1. Okay, so that's how we define the Mobius strip, okay? Well, yeah, okay, basically. Okay? So, in general, if we have this quotient space with the tilde, not just the a, we still have the function pi, which takes you from x to x mod tilde. Okay? And pi of x maps onto the equivalence relation that it should map onto, right? And open sets are defined in the same way. So U, a subset of x mod tilde, is open if the pre-image, of U is open. Okay, so now I'm going to prove something called the gluing lemma. Okay, so the final thing we're going to prove in today's video is called the gluing lemma. Okay? So what it actually states is, let T be a topological space. Okay, so let T be a topological space. So now that T is a topological space, such that there exists closed subsets of T. Okay, there exist closed subsets of T, U sub 1, U sub 2, all the way up to U sub n. They're closed subsets of T such that they cover T. Okay? Now, if S is any topological space, okay, S is any topological space, this means there exists a family of functions, f sub I, which goes from U sub I to T, to S, to S, okay, where I runs from 1 to n, okay, and f sub I of x equals f sub j of x if x is in the intersection of U sub I and U sub j. Okay? Now, what the lemma states is these functions can be glued together. Okay, so the functions can be glued together to make a new continuous function f, which goes from s to t. Defined as f of x equals f sub I of x if x is in u sub I. Okay? Wow. Also, I know what you're thinking. How come my green pen is working so well? Well, it's because I got a new green pen for you guys. Okay? So yeah, now the proof. Goes as follows. We want to show that T is homeomorphic to Q, which is homeomorphic to Q, which is the quotient space, here's where quotients come in, okay, which is equal to, alright, U1 disjoint union, so on, so on, so on, all the way up to UN. Okay, with the equivalence class tilde on it, defined as x tilde y if, okay, x is tilde y if h sub I of x equals h sub j of y, where h sub I goes from u sub I to t, and h sub j goes from u sub j to t, and they're the natural inclusion mappings. Okay? Now, D, okay, is the disjoint union between all of these bad boys here. Define G, which goes from D to T, okay, as follows. G of x is equal to h sub I of x if x is in u sub I. Okay? Now, because G respects the equivalence relation, this means that there exists G bar which goes from Q to T. Okay? And also, this means that there exists G bar inverse, which goes from T to Q. Okay? So now what we want to prove, because this is continuous and bijective, we want to prove that G bar inverse is continuous, and hence we'll have arrived at our desired homeomorphism. Okay? So, G sub bar inverse, okay? Now, a function f is continuous if the preimage of a closed set is closed, okay? That's technically a theorem, but I'll just consider it like an alternate definition, okay? So yeah, what we're going to do is let V be a closed subset of Q, and then show that that is closed. Okay, so G bar inverse of some closed V is actually equal to the image of V under G, okay? Okay? And by construction, this is equal to the union of U sub I intersect V for all I, okay? This is closed, the intersection is closed, the union over finite, the finite union over closed stuff here is also closed, therefore this G bar inverse is continuous, therefore G bar is our homeomorphism. Okay, and this concludes the final video on point set topology, and this marks a very exciting turn in the series. I feel that we've looked enough at some basic ideas in point set topology which are important to know, and now we're going to move on to the spicy stuff. We're going to be moving on to algebraic topology. So next video we're going to be looking at some homotopy theory. And I'll see you then. Goodbye.